Okay, so we'll be beginning with the section 1.6, which is conditions for equilibrium. I hope you remember some of the things which we had learned before, so we'll just take it from here. So if you have a particle on which several forces act, it is the necessary and sufficient condition for the particle to be in equilibrium is that the summation of all these forces should be equal to 0. So for a particle, you have F1, F2, and so on forces. This can be written as a summation. This has to be equal to 0. Now this we already knew, and this is a condition for equilibrium for this case. For our course, we are normally interested in a whole system, okay, and that we can see in terms of isolated system of particles. So as we had discussed in the last class, you will have this whole system to be in equilibrium when the sum of external forces on system is equal to 0. So this is something which we had discussed in the last class, and we had also seen, so this was called equation 1.5, as I had told you to remember. This was 1.5, and 1.6, if you recall, was that the summation of all the moments of the external forces also has to be 0, and this moments is about any arbitrary point. So the point is not specific, like it does not have to be the center of mass of the system. So you would have okay. So Rj is the position vector extending from that arbitrary point O to an arbitrary point on the line of action of the external force. So this was 1.4, 1.5 and 1.6. So this is essentially the force equilibrium, the moment equilibrium, and both of them have to be true. So this is what you have in front of you, the figure 1.12, which shows you a system of particles, and you see that we are only considering the external forces when we discuss equilibrium, not the internal ones. Internally, whatever can happen, it's not our concern. Okay, so 1.5 and 1.6 are called the necessary conditions of equilibrium. Okay. Now there is a sort of a converse problem also, okay, which we must discuss just so that our concepts are clear. Suppose you know that the external forces acting on a system of particles satisfy both 1.5 and 1.6. Can you then say that the constituent particles are in equilibrium? Okay, so consider this case 1.13. See, the summation of external forces on this system are 0 because F and F are of a similar same sign, opposite sign, and the moments of these two external forces will also be 0. So this system will satisfy 1.5 and 1.6. But can you say that, can we say that every one of the constituent particles are in equilibrium? Okay, the answer to this question is clearly no, and that you can see in this particular figure. In this figure, you have a system of two particles, and then the internal force between them are Fi and minus Fi. They are also in equilibrium set, but the particles will be in equilibrium only when F is equal to minus Fi. So only when this is equal to this and this is equal to this will the particles be in equilibrium. So the converse problem is not necessarily true. Okay, that is something which we have seen. Okay, so we have seen all these facts, and we also discussed about the concept of continuum in our last class, so we are not going through that. Okay, for our course we only study a continuous solid. Another very important part, and actually a special case of 1.5 and 1.6 is what we'll be studying next. Remember 1.5 and 1.6. 1.65 is that the resultant of all the external forces has to be equal to 0, and 1.6 is the resultant of all the moments about any arbitrary point for a system has to be 0. So both of them have to satisfy for the system to be in equilibrium. Okay. Let's now see a special case in which you have two forces. Let's say figure 1.14. Let's call it a two force member. So in this figure 1.14, there is a system. What is the system? This is the system in the gray part, which whatever you see around. Okay, so this is the whole system. It's a continuum solid. Okay, it's a continuum solid. So they have two and only two external forces acting at points A and B. It's clearly shown FA and FB are acting at these 2 points, external forces. The two forces now cannot have random orientation as shown in this figure. So you cannot have, if this is in equilibrium, this continuous solid is in equilibrium, then these F1 and F2 cannot be, FA and FB cannot be random, and they must be directed along the lines AB like this. What does this ensure? It ensures that the 1.5, which was the forces, have the resultant of forces has to be same, so FA will be equal to minus of FB. Okay, and how is 1.6 ensured in this case? The moments which you take, okay, will be 0. So the summation of all the moments which you take about any arbitrary point. So you can verify this. What do? Find the moments about point A, calculate, then find the moments about B and then calculate. Okay, both of them must come out to be 0 in a situation like this. Okay. So this is called a two-force system, and you will see that most of the solids which we deal in our course are not these random shapes. Okay, they will be like a bar or a cube or things like that. But as soon as you see a situation like this, of a two force member, you should be able to recall what we have learned. And this is all done so that 1.5 and 1.6 are satisfied, both of them, which means that the system has to be in equilibrium. Similarly, consider a three force member. So in figure 1.15, you have a system which is in equilibrium. I mean, it is told that it is in equilibrium, and the action of, there are three external forces acting at A, B, and C, as you have seen. Now, just like in the previous case, they cannot have random orientations. They must lie in plane A, B, C if the total moment about each of the points is to vanish. Meaning, you calculate the moment about A, okay, summation of all the moments about A, summation of all the moments about B, summation of all the moments about C, and they must be equal to 0. This can only happen when FA, FB, and Fpsi lie on the same plane. So this is very similar to this situation which you have. Okay, so this is essentially trying to satisfy 1.6. Okay, now they must also intersect at O. Okay, and because if it does not do, the total moment about the intersection of any two of the lines of action could not vanish. You can do this exercise yourself. Try to take a case in which they don't actually intersect at O, and then you will see that you are not able to vanish the moments due to the external forces. Okay, so these are the few things which are there, and you can take some special cases. I mean, in the case when O is very far from ABC, how do these forces look like? Okay, if O is very far from A, B, C, then what happens? Okay, so these are situations which you can think about and see whether it matches with your understanding so far. Okay, so let's move ahead to something called general coplanar force system. Now if you look at figure 1.16, again, see, we draw these ugly figures of the system. Okay, you see there, I mean, these random bad looking figures, just so that we are not constrained by whether it's a circle or a square or a triangle or whatever nice shapes which we have, because these concepts are very general. That's why we take these ugly shapes all the while. Okay, so that the geometry is no longer a constraint for us. Okay, so let's look at this system, and you have external forces which are clearly shown to you, and they are the forces lie on a plane, lie in the plane. Okay, so we are doing this because it is easier to understand and apply 1.5 and 1.6 if it's in a plane, because automatically the third dimension does not play much role over there. So there's a reduction of the number of unknowns. You'll see that. Okay, so forces all lie in this plane, the plane of your screen right now. So in this case, 3 of the 6 general scalar equations of equilibrium are immediately satisfied. There are no force components lying perpendicular to the plane, and if moments are taken about a point O lying in the plane, so this is the point O lying in the plane. If you take moment, the only moment component will be perpendicular to the plane. This leaves only 3 independent scalar conditions of equilibrium for two-dimensional problems. So how many conditions are originally there? Can you think of? I mean, in a truly three-dimensional case, how many independent scalar conditions of equilibrium are there? Sorry, not. What is 1.5 and 1.6? Okay, in a truly 3D case of equilibrium, how many independent scalar conditions are there? Okay, the answer to this question is clearly 6. There are 3 force directions, force conditions, okay, meaning the sum of forces, external forces along the x-axis has to be 0, the sum of forces along the y-axis is 0, the sum of forces along the external force along the z-axis is 0. Similarly, there are 3 moment conditions, each of the directions. Okay, so this is for a truly three-dimensional case. Now, if you want to sort of see this for, I'll remove some part of it. Let me just do this over here. Now, if you have a system in which you have planar forces, I mean the forces are lying in the same plane, then clearly you don't require these 6 conditions of equilibrium, and hence your problem will be much more simpler. So you are, for this system, for planar system, you have only 3 conditions. What are the 3 conditions? 2 forces, say along the x and the y direction, which is given sigma fx equal to sigma fy equal to 0, and 1 moment, that would be sigma mo equal to 0. So the moment will only be along the axis which is perpendicular to your screen. Reason is all the forces which are causing this are lying on the plane. So an r cross f will always lie perpendicular to the plane. So that's why you have only one direction and hence only one condition of moment. So that makes it only 3 conditions. So O is your arbitrary point, okay? And if you look at this figure very carefully, every external force, say Fj, can be broken down into an x component and a y component. Okay. Similarly, every position vector can be, like position vector lying over here, can be broken down into xj and yj. Okay. So this is how we have written the notations on this figure. And if you write the vector sum of the external forces for this system, which was 1.5, if you remember, that would give you, this was 1.5, sigma fj will be equal to sigma j fjx I cap plus fjy j cap, and this must be equal to 0. This would imply that sigma fjx is equal to 0. Remember, fjx is a scalar, okay? I cap and j cap are vectors, fj is a vector, but fjx and fjy are scalars over here. So this is equal to 0. Similarly, fjy is equal to 0. This is called 1.7. 1.7, as you see, is a special case of 1.5 for coplanar force system, when all the forces are lying in one plane. Okay. Similarly, you can write 1.6. Okay, let me just remove this. So 1.6 is essentially the total moment about O should vanish due to all the external forces. So that would mean that you have a summation J and Rj. R is the position vector from O to the point of application of that external force, and that external force is Fj. Okay, this can be written by writing the position vector as xj I cap plus yj k cap cross fjx I cap plus fjy j cap. Sorry, this is j cap, not k cap. Okay. Now, if you take this particular cross product, you will find that the k unit vector can be taken outside, and jx j f j y minus yj f jx is equal to 0. So this is the condition 1.8. 1 point again is a special case of 1.6 for a coplanar force system. So we will be referring again to 1.7 and 1.8 very often. So I think it's a good time to remember what 1.7 and 1.8 are. So 1.5 is the, for equilibrium, the summation of all the external forces on the system is 0. 1.7 is a special case of it for a coplanar system. 1.6 is the summation of all the moments about an arbitrary point is 0 for all the external forces, and 1.8 is a special case of it for coplanar system. So 1.5 and 1.6 essentially means 6 conditions. Okay, we have discussed this, but 1.7 and 1.8 only mean 3 conditions to be satisfied. So we will be using these conditions in our problems. Okay, so let's see. So let's now sort of take up a example of which we can study. So this is something, the site which you see over here is something which you may have seen at some point in your life. It's an external unit of a split AC. Okay, and it is standing, if you see, on something called a triangular stand. Okay, because of this shape which you have, this is called a triangular stand. And there are many other situations where such stands exist, and we are taking up a problem which is somewhat inspired by this. I mean, not exactly this, but somewhat inspired by this. And an important part about this problem is that this problem continues throughout until the end of this course. Okay, so I request you to be focused when we discuss this problem at this stage, so that you can track the modifications which we keep on doing and the newer concepts which we keep on learning through this problem and perhaps the next problem as well. So let's see what that problem is. You have a simple triangular frame which is shown in figure 1.23. Okay, this shows you a single triangular frame, and then it is used to support a small chain hoist. So this is the chain hoist and it is supporting that. You are asked to predict the forces acting on the wall at B and C. So you have to find the forces acting on the wall at B and C when the chain hoist is supporting its rated capacity of 20 kilonewtons. The rod BD is pinned at its end. Okay, so B and D, it is given in the question, there is a pin joint over here. Okay, and the member CD is pinned at D. So if you look at CD, it is there, it is joined by pin over there at D, that is given, and secured with 4 bolts at C. So you can see there are 4 bolts at C, 1 2 3 4. So this is how we have how this triangular frame is set up. Now there are few, so we'll solve this, and we will not, I mean it's a solved example of the book, so we won't go into the maths of it, but we'll definitely go into a discussion of the reasoning for all this, because until now you have been solving almost all of your problems straightway by simplifying and taking assumption, which we will also do right now, but it will also give us a motivation what thought process is required to make our treatment more closer to reality. Okay, and why we take assumptions and when should we take an assumption. Okay, so let's go through that thought process. That's why we are discussing this over here. First thing is that you want to sort of first make a first attack on this particular problem and see how it goes. So if you look at figure 1.23b, okay, what it does is it has an 1.23b shows you a isolated, sorry, 1.23b, this figure, okay, it shows you an isolated free body diagram of the frame. One thing to note, that system is not rigid, meaning the system can definitely move around, right? I mean, once you say push the point B down, point B down, I mean it can all deform and even collapse. Okay, so itself it will collapse by itself. Collapse. So, and I mean, you are very most welcome to actually see whether it collapses. What you do is just take 2 pins, make a horizontal CD, make a horizontal BD, and then just leave it, right? If you leave it, we don't apply any force, the system will collapse due to its own weight and the way you have joined them. Okay, so that is what it means by the system will collapse. Now the whole point of this stand, this air conditioner which we are able to hold, is that there are certain forces and moments which are applied which do not allow it to collapse. So the external forces F, B, F, C and MC are sufficient to prevent collapse. Okay. Okay. So we have, I mean, we have already taken FB, FC, and so on, and with this it does not collide. Now there are some assumptions which we are making and some things which we are neglecting, and we will make a note of it. It's important to note down the assumptions and anything which you are not considering, and it should be very clear for a person who is trying to read your answers or trying to because only then he or she will be able to understand what you are actually thinking. Okay, so at this stage, neglect the weight of the frame. Okay, this is how we are proceeding forward. Now the only force and moments force and moment interactions which are happening are at B, are at C, and are at D. Okay, if you neglect the weight of it. Otherwise, I mean, you would have to take the weight of each of the rods or for the frame as a whole. But now the only interaction which is this is having with the outside world is through B, C, and D. Okay. Now at D you are showing a vertical load of 20 kilonewtons. Okay. This is something which you are showing because it is given as a part of your question. At B there is a pin joint. I mean, we know that because it's given in the question that at B there is a pin joint. And so B has a pin joint. Okay, now you may have learned about different kinds of joint in mechanics in your first year course. If you don't have, if you haven't learned it, you can still go back to table 1.2 of your textbook, this textbook, okay, and see what a pin joint is, okay, and then it will tell you about an assumption. So if you look at table 1.2 and see, it tells you that if you have a frictionless pinned joint, then it can be seen as a force which passes through the pin. So, and then it also says that there is no torque about the pin. So it is referring to a frictionless pin joint. Okay, so you will have just say a force. So if this is your pin, so all it tells you is this F. So there is a force which is drawn, which passes through the pin, and there is no torque about the pin. No torque is transmitted. So this is what we have from table 1.2 and C, 1.2C. Now, in the question which we have, do you see that there is any evidence or hint given that friction is not present in this question? You can read the example 1.3 carefully and see whether there is any indication whether friction is present or absent. Okay, so you may have figured out that there is really no indication in our question that the pin is frictionless. Okay, so what we'll do is this: we will we will consider the most general case in which at B, okay, at B there could be a force in all three directions. Then you can have moments or torques in all three directions. So this is the most general case. But since it's a planar problem, okay, all the since the frame lies in a single plane, the plane of your screen, and the load which is D, okay, 20 kilonewtons is also lying in the same plane, it is reasonable to expect that all forces of any consequence will also lie in this plane, meaning FB, FC, all of them should lie in the same plane. So FB will lie in the plane. Okay. So this is a expectation through which we have said that FB lies in the same plane, and hence automatically you will have only two forces and one moment to take care of it right now. Okay. Now we want to now check how and if it is possible to ignore moment due to friction at pin joint B. So let's consider this pin. This is the pin. If it did have friction, okay, say the joint is like this, okay, and if there was some sort of a friction on this pin, then the moment due to that friction will be equal to F times N, which is the normal force. F is the friction of coefficient, and small r is the radius of pin. Okay, so this is this moment at B. Okay, now so we have found actually the value of the moment due to friction at the pin, and now we will take one more sort of consideration. Now if you go to problem 1.10 in your textbook, this is like an equivalent force system which you had learnt again in your first year mechanics course. So what it tells you is that if you have a system at which you have a force, then you have a moment at the given point, this is equivalent to having a force at a distance A from this original point A. Okay, and you can check this problem and see what are the steps which can be taken to transform from here to here. Okay, I mean, just for your information, you may have done this. What you do is you take at a distance of a point, apply a F over here, apply a F over here, so that there is no net force, and then you can get rid of one of these couples. Okay, that will cancel out the moment, and then you will be able to get that. So this is something which you can do. This is problem 1.2. I'm sorry, I should have. Okay, this is the same solid. Okay, and the distance, this A is actually a measure between M by F. Okay, so this is can be done. So this now when you apply to your system, which is at A, at B you also have a force and a moment due to friction, and this is equivalent to a single force displaced sideways. So you have a FB, you have a moment due to the friction at B, and they act at the same point, which is the pin, or say the center of the pin. And so this can be this system of one force and one moment can be balanced, can be taken as an equivalent to only a force which is displaced by a certain distance. Now look at this number over here. This is typically, if you take 1 by 3 as a friction coefficient, you can always check a table and see what are the ranges of friction coefficient, but 1 by 3 is a reasonable number to take. Now what will this do? This will, sorry, this I should have written it with a capital F. Sorry, no. And this N will be equal to FB. So if you want to find for this pin system how much this force, this displaced force will act, it will be 1 by 3 F R by F. I'm just taking the vector forms, okay, and that would mean that it would be R by 3 as a maximum case. Why maximum? Because you are assuming over here, when you write the friction to be acting in this form, you are assuming that friction act at its maximum value. So you are taking the worst case scenario. So this means that the greatest effect of friction at the pin B would be to displace FB sideways 1 by 3rd of the pin radius. This can be neglected because pin is very small and 1 by 3rd of that radius will make it much smaller than any other dimension. So that is why you can neglect the moment due to friction in a pin joint. Okay, so you could have said, well, we could have taken it, neglected it at the start itself, but as I have told you, in this entire course we have to follow a thought process of why something can be neglected and why not. So that is how you are able to neglect, because at worst this FB will be displaced by this distance A, and worst I say because of its maximum friction assumption which you are taking. In reality the friction may be acting lesser than that. Okay, anyways, so that's how you neglect this. And now you come to C. So this was all discussion based on this point at B over here. Now I'll have to sort of rub this part out. As I've said again, this problem will keep on coming throughout the course, and it's very important for us to familiarize with the reasonings which we do over here. Okay. So what we have learned until now, that if there's a pin joint, you can ignore the moment due to friction and just take a force, irrespective of the fact whether there is friction in the pin or not. Okay, now let's come to C. So there is a bar CD is joined to the wall by 4 joints. So you can see that there are 4 bolts which are joined. I mean, this is where you can see that. And this leads us to a conclusion that there must be a force Fc. Of course, Fc has to lie in the same plane, just based on the previous reasoning. That since the frame lies in the plane, the only force D at D lies in the plane, hence any force of consequence must lie in the same plane. So this is how we have said that Fc lies in the plane, and then there is a moment mc which we have taken over here, which uh, is acting over here, and the purpose of this moment is that it does not allow a free rotation, and we are not excluding this moment because we are sure that this is not the pin. Okay, so the constraint which a bolted joint will have will be much more than a pin, so you cannot ignore this moment over here. Okay, so let's go back to 1.23b, and in this one you have two unknown force vectors. So in this one you have Fc, Fb, okay, and Mc, which is unknown. So what are the unknowns in this? Let's see. Fc will have two components, right? In x direction and y direction. Fb will have two components, and Mc will have only one component, which is perpendicular to the plane. So there are in total 5 unknowns. Okay. But for a coplanar system, of equilibrium, how many conditions do you have? You have only 3 conditions. Okay, 3 independent conditions are available. So you have 5 unknowns and 3 conditions. So you cannot solve them right away. Okay, now you must get some additional information, and that additional information you will get by this diagram at C. So if you look at C, you will have we have isolated 1.23c. You have isolated the bar BD, and you want to draw a free body diagram of it. So you have already known that if there is a solid and then there is a force which is say FB and FD, if this bar has to be in equilibrium, then these forces cannot be arbitrary and they must lie in the same, okay, along the same line. This was, if you recall, the two force member, and one other condition is that FB must be equal to FD in magnitude and opposite in direction. So this was a two force member which was there, and that is why this diagram 1.3c has come up. Okay, now you can come to, so you have actually got one condition now, but you still need one, let's see, one more. So if you go to 1.23d, you show 1.23d over here. you show now the free body diagram of the bar CD. So you have isolated the bar CD over here, and you are showing all the forces. So you have FC, you have MC, you have minus FD and 20. So remember, at this you have FD acting. So on the same joint you will have minus FD acting. Okay, so this FD, so there you have minus FD, so that the spin joint at D is in equilibrium. Okay, so the direction of FC still is unknown. I mean, it can be, we know that it's in the plane, where it can be anywhere. And the magnitudes of MC and FT, so what are the unknowns? So you have FC, you have FD, and you have MC, okay, for CT. Let's see. So this can have two unknowns. FD. What is the unknown in FD? So you already know the direction. Okay. So you have only essentially one unknown over here, and this is also one unknown. So you have four unknowns now. This has come up after you have used this C over here. Okay, so you still have four unknowns, but you have got three independent equations. Now the direction of FC still remains an unknown, and you have this situation where you have actually gone or done all possibilities, which you could have isolated everything which you have. I mean, you had two rods, you have isolated them, was first this and this, and you are still stuck with this. So you have four unknowns, three conditions. You call this situation as statically indeterminate. Okay. So since you cannot solve for four unknowns using three equations, so we will see in the next class how we can proceed next in a situation like this. Okay. Thank you.